As promised, we'll be looking at Kolmogorov Forward Equation in this particular video, still on continuous time Markov chains under the stochastic processes playlist. We've mentioned Kolmogorov Forward and Backward Equation in the previous videos in passing. Now we'll look at the forward equation in some depth. So Kolmogorov Forward Equation, or for the continuous time Markov chains, right? The Kolmogorov forward equation describes how probabilities evolve over time in a continuous time Markov process. So let Pij of t at it be equal to probability x of t equals j, given that x of 0, x at time 0 is equal to I. This represents the probability of being in state j at time t, given the process started in state I, right? So here we talk about the continuous time Markov chains as a kind of refresher, because we've been talking about it in the starting from the last two videos. So a continuous time Markov chain is defined by a state space S, which is 1, 2, 3, and all that. Then you have a generator matrix Q, Qij, and you have properties of the generator matrix Q. Every Qij is greater than or equal to 0 for I not equal to j. So every off diagonal value is non-negative. That's what that means. And then all the Qi's are minus summation of j not equal to I of the Qij's, like that. Now we talk about the transition probability matrix, which we've been talking about for the longest. So let P of t be equal to Pijt, like this. This matrix contains transition probabilities between all states over time, and it is usually defined as the exponential matrix involving the generator matrix Q. So I'm talking about the Kolmogorov forward equation that this video is really about. The main equation is that d dt of p of t is equal to p of t multiplied by q. So the positioning of this q is what distinguishes the Kolmogorov forward equation from the backward equation. For the backward equation, the q comes before the p of t. So you have qpt for backward, p of t q for the forward. So, and then in component form, you have that d dt of pij of t is equal to summation over k of pik of t multiplied by qkj. The interpretation is this, that the equation represents probability flow. That is, probability flows into state j from other states, and then probability flows out of state j to other states. So this gives the rate of change of probability in each state. So that's talking about the rate of change of probability in each state. So if you have an example like this, for a two-state system, if you consider two states, 0, 1, so this is state 0, this is state 1. You could as well say state 1, state 2, anyhow you want it. So that's 0, 1, 0, 1, like that. So moving from state 0 to 1 will require rate lambda, and moving from state 1 to 0 will require rate mu. That's what this means for the generator matrix. And when you add the generator matrix, each row sums to 0. That's minus lambda plus lambda is 0. Mu minus mu is 0, like that. So for the forward equations, then you have this, that if you let P naught of t, so if you let P naught of t be equal to probability that x of t is equal to 0, and then P1 of t is probability that x of t is equal to 1, then it means that the P naught dt will be minus lambda P naught plus mu P1. So you see, based on this now, so minus the rate of change of P naught of t, that is moving from state 0 to 0, that's minus lambda. So you have minus lambda P0 plus moving from state 0 to state 1, from state 0 to 0, you have this. From state 0 to state 1, that's P naught, right? X of t is 0. So that will be mu, okay? From state 0. So from state 0 to state 0, this is it. From state 1 to 0. So okay, so moving into and out of it. So if you flow into state 0, to remain in state 0, you have minus lambda P naught. To get out of state 0, that's from 1 to 0 now. From 0 to 0 and from 1 to 0, that's mu P1, right? Then for P1 PT, so moving from state to move into state P1, right? To move into state 1, that you move into state 1 from state 1 to 0, that's lambda P0, and from state 0, to from state 0, yeah, from state, okay, this one is from state 0 to 1, that's lambda p naught, and to move out of state 1, that's from state 1 to 0. So from state 1 to 0, that is minus mu. So it's like you're coming out like that. So that's minus mu. This is 1 to 0 now. That's minus mu p1. So, and once you have that set up, so you have a system of differential equations now, which can then be solved. So if you use P1 of t, if you take P1 of t to be 1 minus P naught of t, that means that the P naught dt is equal to minus lambda mu p naught plus mu, if you solve all of that, because for P1 of t now you're taking 1 minus P naught here. So you have the P naught of dt is minus lambda plus mu P naught plus mu. So then if you solve all that, you get P naught of t to be this very complicated solution, right? So, and but you can then simulate all of that. So you have the PD1 minus lam P naught plus mu P1 and all of these things. So if you simulate that now, you get something like this. You see that xt equals 0, that's coming down, while p xt equals 1 is coming up. So the probability for for state x equals 0 is reducing, while state x equals 1 is increasing, like that. Then you can then still talk about the matrix form solution. So for the forward equation, the pt dt is p of tq, and it has a solution that p of t is e raised power qt. If you remember, our probability transition function or matrix is given as e raised power qt. This is how we got it. So this is more like a proof for getting this, because if you solve this now, so this is more like you have the p of t dt. The Kolmogorov forward equation itself is this, that the p dt equals pq. So to solve for p now, so it means you can do separation of variables. So the p all over p is equal to q dt. So if you integrate both sides, so integral of the p equals integral of q dt. All right. So that means integral of dp of p is equal to q, which is not a function of t, dt, like this. So integral of dp of p is ln p, ln p like this, equals qt, right? And to get rid of ln, so you have e raised power ln p equals e raised power qt plus some constant, from constant k, if you like. So now this is basically p equals e raised power okay, when we integrated, right, the k should have been here. This is plus k. So we can have the k here better. So we then have p now to be e raised power qt plus k. So, and then this is like p equals e raised power qt times e raised power k. So that means you have p to be, so if this e raised power k is now like a constant, if you like, call it c1. So you have c1 e raised power qt. So if you then have something like, this is fully p of t equals c1 e raised power q multiplied by t. Okay. So if you then say that if p if p0 is equal to 1, all right, this is t, sorry. If p0 equals 1, that's the initial condition now. That means that at t equals 0, then p is equal to 1. That's what that means. So we then have that on the left-hand side now. So we then have that p of 0 is equal to c1 e raised power 0. eq, sorry, I've also skipped the key here. So qt, eq into 0. So that means p of 0 is equal to c1 e raised power 0. That means that p of 0 is equal to c1, because e raised power 0 is also 1. But then p0 is 1. So that means 1 is equal to c1. So we can then say, since C1 is equal to 1, what that simply means is that we can come back here and say that P of t is equal to C1 e raised by QT. That is, C1 is 1. So that's 1 times, that's C1 e raised by QT, right? So that means P of t is equal to 1 times e raised by QT. So that means P of t is equal to e raised by QT, like this. And that goes. So that's how we got P of t to be actually this. So that's like from the forward equation. That's very possible to get. So then we keep moving. So this is the matrix exponential, which we've been talking about before. So, and we can always simulate that to get, so for this minus to get, we can use this now to get the probability distribution, right? So for any given Q, so for -2 to 1, 1, so you have this as usual. And, if you increase the time, you can have an idea of where this is going to converge to. So the way this is now, it may be difficult to see clearly what that might look like. But if I make time 10 now, so it's already, yeah, you can see it's converging. So if I make it like 10,000, you see that it's most likely going to still be something close to this, yeah, same thing. So that's what that looks like right there. So, and then we talk about the Bethe process example. Bethe process example. So a pure Bethe process satisfies that Qn comma n plus 1 is lambda, while Qn is minus lambda. So that is moving from a state to the next state is lambda, but remaining in the same state is minus lambda. So that's the Bethe process. And then for forward equation, we then have that d dt of Pn of t will be minus lambda Pnt, all right, plus, plus lambda Pn minus 1t, like this. So minus lambda Pnt plus lambda Pn minus 1t. So with that in place now, then we can talk about the Poisson process solution. If starting from state 0, we have Pn of t to be lambda t raised by n raised by minus lambda t over n factorial. That's the Poisson process, which you've also seen in the previous video. So in this case now, if you have lambda to be 3 and time is 2, and you do the probability lambda t, you do this whole thing for n in range 10. So if you do it for 0, 1 up to 10, you get this whole, so you get different values. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. In fact, I may want to have this, I can say, I may want to tabulate this so it can be clearer. So I want this to be tabulated. Okay. Tabulate solutions. Tabulate solutions. And then we have that right there. I want the solutions tabulated instead of just spreading out like this. Yeah. So I think this works out properly now. Okay. Saying that no props defined. Correct errors now. Correct errors. Correct errors. So we're waiting for the correction of the errors. Let's hope this works properly. Yeah, so this is it now. We have all the errors corrected. So now all these things that you're seeing 0.16, 0.1606, and all the okay, yeah, we started from 0.0024. You can see that here, 79, 0.14. So you see all the 10 probabilities now starting. So because we said it should go from 0 to 10, right? So in fact, I think I could actually then if you sum up all the probabilities now. Okay, I guess I want to carry the sum here. So print props and then, okay, well, I can just leave it. So if you sum up all the probabilities, it's like 0.91 something something. But this is the tabulation of all that now. So in vector form now, we have all of that to be this, let the probability vector be pt equals p1t, p2t, Then the ddt of pt is ptq for the forward Kolmogorov forward equation. So, and like I was saying the other time, forward versus backward equation. Forward equation, you have the pdt equals pq, and backward equation, you have the pdt equals qp. So it's about the positioning of the q of the generator matrix. So for forward evolves probabilities forward in time, and backward evolves based on initial state. Okay, so in summary, we see that the Kolmogorov forward equation is d dt pit of pij of t equals summation over k of pik of t qkj. And the key points are it describes probability flow in continuous time Markov chains and forms a system of linear differential equations and fully determined by the generator matrix Q, and solution uses matrix exponentials. So we then have some practice problems. So given a two-state continuous time Markov chain with rate lambda equals 3, mu is 2, write the generator matrix Q, so we have that. Then, okay, did we really touch on this so far? I doubt it. Ah, okay. I think it's possible for a two-state, right? We have lambda and 2 like that. So I think it's going to end up being something like this 3 and 2 thing we were having the other time. This lambda, yeah, this minus lambda and mu minus mu. Okay, so that's the kind of thing we're going to have. Minus lambda mu minus mu. So it's going to be like minus 3 3, then 2 minus 2. So that's what that's going to be for that kind of for those values. Then for the generator matrix, Q equals minus 4 for 1 minus 1. Write the forward equation for P naught of T and P1 of T. So we're going to follow what we had here now. So just follow exactly this thing here. All right. This expression right here, minus lambda p naught plus mu. So that's minus lambda p naught plus mu. So you come this way and then you come this way. So this is like minus 4 4, right? That's minus 4 p naught plus uh p1, then 4 p naught minus p1, because lambda is 4 and mu is 1, like that. So we want to follow all of that and see how it goes. So go through the questions and see how well you can take care of those things like this. So, I mean, this one talks about verify that the rows of any generator matrix sum to 0. I think we've talked about this a lot. Problem 4, P naught of 0 is 1, P1 of 0 is 1. Solve this now. Okay, you have an initial equation and you want to solve this. Then problem 5, show that P naught, so I think the way to go here is to use the idea that P naught of T plus P1 of T is equal to 1 for all T. So in this case now you could just say, instead of having P1 here, you now have 1 minus P naught, and you tidy things up, and then you can easily solve this based on the initial condition right there. Then find the stationary distribution for this. Okay, that's pi q equals 0. Then compute P of T equals e raised power qt. You can do that too. Write the component form of the forward equation for a three-stage system. Then for a birth process with rate lambda, write the forward equation for P2 of T, and so on and so forth. So you want to try out all these questions to see how well you understand. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed already, I thank you very much for doing that. If you haven't subscribed, what exactly are you waiting for? Go ahead, subscribe, and hit the notification bell so you can always get alerted each time a new video is released. Um, Ultimately, don't forget to you can also become a member of the channel, by the way, by clicking on join. That gives you some special privileges, like you can get to see some videos first, and you can also be the only one seeing some videos exclusively because you're a member of the channel. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. um Till I come your way again, keep doing math right. Bye.